So I'm going to talk tonight a bit about what we do at Zesty AI. In particular, what we do is we help people understand property risk, both residential and commercial. And we focus in on catastrophic loss areas, such as the wildfires that we all saw on the West Coast, particularly California, which lost over 4 million acres last summer. Season just barely ended, actually, fire season. That's twice the previous record. And we're also looking at other threats, such as hail. Hail is actually the number one loss, particularly against residential property in the United States. We're focused on the United States market. Our company is, though we will address other markets in time. Where other things we're interested in for catastrophic loss are things like convective storms, which can include hail, strong winds, even hurricanes, though we're not a hurricane company, and floods. But all these things have in common is that we're really interested in understanding at an individual property level, an individual house, what will that house experience? And that's very different to what's been done traditionally in the past. Over the last 50 years, we've seen a tremendous growth in the losses associated with these events. Now, one could argue some of that is because people moved into areas where it's more risky. Could be true. California, some people have shifted away from the cities up into the foothills and beyond because the price of housing, like in the Bay Area and even LA and other areas. But there's no question that the losses have escalated. And if you look at the type of data that we need to understand these losses, traditionally, it has been using science-based models, first principle models. Some people would argue heuristic-based models, trying to model nonlinear events like hurricanes, fires, floods, hail. Very difficult. Now we have a new option, which is we can use big data. So we can actually use data from many sources. And we'll talk a lot more about that shortly. I see one question popped up about earthquakes. No, we don't predict earthquakes. We don't predict volcanoes either. There's some things we don't predict yet. Tsunamis also, we don't predict those. But who knows, someday maybe. But in our case, what we're really interested in is how to get the data, how to analyze the data. We use cloud, we use all the major platforms. And we're really interested about offering these insights to our clients, which are traditionally big insurance, reinsurance, and people of interest, such as people that sell housing products to builders, roofing materials, and so forth. Many companies have been very successful in using data, as we all know. Amazon, of course, is the obvious one. From the middle 90s, it started in Seattle. I know them well. We also have seen successes in recent years, like Lemonade, Hippo, and of course, who can not notice Tesla, what they've been doing, 6-fold this year in stock appreciation. Our company has been at this for a few years. And what we're doing is we're using data from multiple sources. The traditional sources, of course, things like building permits and things like that, but that's really not what we do. What we're really interested in is understanding visual data and multispectral data. So we're dealing with data from airplanes, low Earth orbit satellites, drones. We process it in the cloud, and we use a lot of AI-based data science technologies, deep learning, machine learning type things. As you probably have noted over the last couple of years, even, the abundance of this type of data has grown greatly. Now insurance companies come to us to understand things like wildfire because we have more data than they do. They don't have all the losses for the fires in California. They have the losses for the company, the houses they insured. And in the insurance industry, you look at the top 100 insurance companies in the United States, even the biggest is only around 20 some odd %. And then it goes down from there. So they don't know all the fires that occurred in California. And they would really like to understand that better. Also, like in California, what's going on is that they're letting them literally not uninsure these people. They're now putting laws on the books, and they're holding their feet to the fire in terms of you can't just cancel a policy. So then how do they deal with that in a correct way? And also they want new insurance companies to come into California and other places to insure, but they have to do it within the framework that exists. So what type of data do we deal with? As I mentioned a minute ago, we're dealing with multispectral data, all the visible spectrum, near IR. We're dealing with different ways of processing the data, certainly doing typical visual deep learning, identifying does your house have a pool, does it have what type of roof, the shape of your roof, artifacts about the property. Also, the footprint of your house is something else that we determine from the properties. We can use also not just optical, but we can use things like LiDAR. So we're interested in digital surface type model data. So we can take data that tells us the height at various grid positions, and then we can determine what we're looking at in 3D. And of course, we have all the traditional sources. And weather comes into play here, and of course, topography. How many houses have we looked at in the United States? Well, right now, it's over 100 million. And we've analyzed these houses, and we've looked at them in terms of characteristics we care about, and including 3D analysis. 3D analysis lets us understand things like what is the shape of the roof, what is the area of the roof, what is the height of the house, how many stories does it have, what is the average pitch of the roof. Pitch is actually very important for things like hail. Also, we'll get more into it, vegetation around the house. What secondary structures are there, depending upon the threat. When we look in a neighborhood, look at a shot around a house, we determine all the footprints, not just the one house we care about from geocoding. That helps us understand these secondary structures and how close another building is to that house and what that means to it in terms of things like fire issues, density comes into play here a lot. If you look at the most extreme wildfire zone, it's of course California, which has about 3.33 million acres of forest. And it has many wildfires each season. This year it had over 4 million acres. So it's more than 10% of it burnt. It's amazing to see that type of fire activity. The models that they've used traditionally in the past, as I mentioned a few minutes ago, are first principle physics models. They've been in the marketplace for many decades, and they don't do a great job, as I'll demonstrate here in a few minutes. And the biggest problem is we're really interested in is how do we take the real data for the real losses, and how do we consume that data and build real models that matter? When you look at all the threats that I mentioned a minute ago, the one that's really obvious to understand is fire. Because if it is a catastrophic loss like the Paradise Fire from 3 years ago, you can see the houses are gone afterwards. So you don't have to guess whether there was a damage or not. Here's a short video I'm just going to play here, but it's very short. But we can see the before picture is shown here. And we can certainly see the after. So it's not tricky to determine the pink are losses, the green survived, orange had partial damage. We can tell at a very large scale, all of California, what is actually going on. We can also tell things about the density of houses, the density of vegetation near the house, wild, forests nearby. How big are they? How approximate they are to the property. And this enables us to do a much better job of understanding the threat that occurs. These are pictures from Paradise. Paradise lost a huge percentage of their city. I think they had numerous people perish in this fire. And this was not predicted ahead of time. And it's very sad when you see these type of events occur. So the question is, what type of data do we deal with? Well, we have over 1,200 wildfire events that we've been able to analyze across North America, particularly the United States. What we're looking at the United States. We have 100 years of wildfire history. We have 20 years of history in particularly North America, which is really our market. And we have 10 years of damage, like what I just showed a minute ago. So we can see the damage, we can see the total losses and so forth. This enables us to get very finite on understanding if we do have knowledge about the exact size of your house, the footprint here, we're determining with deep learning from optical, airplane, or satellite imagery. And we can tell exactly, as shown here, these are results, where the outlines of the bushes are. And based on the peril, wildfire, you don't want to have a tree overhanging your house. That'd be a very bad thing in Northern California. If you're in Nebraska, and you have a willow tree that protects your house on one side, that will actually help you during a big hailstorm. So there's a case where vegetation overhang is a good thing, not a bad thing. So it depends upon the peril as to which one is which. So we're looking at all the shrubbery, all the trees, and because we have also DSM type data, height, as well as we can see the extent. We can tell how tall the trees are. We can tell a lot about that issue that you're facing and assess the risk properly. When we're looking at a neighborhood like this is actual real data for a given case. You can see the full loss cases in pink. Again, you can see the partial loss and the ones that survived. By looking at this across a very large number of houses, hundreds of thousands of losses, you can develop a model which tells you, first of all, we call it L1, which is the likelihood of fire occurring at a given location. Give it a 1 to 10 score. That's what we do in Z-Fire. Then we can also talk about if there is a fire at that location, and if this house is sitting there, what happens to that house? Does it survive or does it perish? And so then you can get a better understanding about how you might want to build a house to survive a wildfire by looking at examples of ones that survived, green, versus ways you don't want to build one, maybe the pink ones here. It's a great example of big data being used well. We talk about areas around the house. We studied 2 different zones within 0 to 30 feet, 30 feet to 100 feet. That may or may not contain neighboring structures and things such as that. All of this is rolled up, and then you can look at real examples. And here is one. This is Sonoma area. Nice wine. This is 2017, the Tubbs fire. The pink here is where the forest is at, basically, forested area of it. The black is largely vineyards, houses. The gray is urban, so cities. You see Santa Rosa right here. The models before all predicted these type of losses right here. The blue are what they would predict for a house perishing in a fire here. Looks reasonable. What actually happened? It didn't stay within the pink boundaries very good, did it? They lost houses in the middle of Santa Rosa. There were people jumping in their swimming pools to survive. So they didn't burn up with the fire. And they spent hours and they got hypothermia because they were in their pool so long. It came all the way into Santa Rosa. Our model does predict that. Our models are able to handle that in this case. So it is a very serious issue that we're looking at here. And I wish I could show you all of our data, but we can't do that in this forum. And I encourage you to ask me questions, and you can see more on our website, and there'll be more things coming out. But we have all these rules and regulations we have to adhere to. But the bottom line is that big data lets you, with data science, really understand what happened. And just like the previous talk, I mean, the only thing that matters is what's actually true. And the truth is in the data here. So knowing what actually has happened in major fires such as this one, and in fact, the fire marshal for this area, Napa area, is one of our scientific board members, David. And he has some pretty wild stories. You realize that, like in California, if you've ever traveled there much, you see eucalyptus trees. Do you think native? They're not. You know what happens when they have a fire and it hits a eucalyptus tree? It explodes and can kill firemen. That was one of the Dave stories. He helps us understand fires better. He was actually in one of the pictures of paradise there earlier. It is a very personal thing when you have to live through these fires. And in fact, in the Napa region, Sonoma, Great Wine, Napa, they have fires all the time in the vineyards. Stag Sleep was burnt to the ground a couple of years ago. May have been during this. I can't remember if it was 18 or 17, but it was burnt. Their main wine area where they taste wine at Stag Sleep, one of the great wineries in the world, burnt to the ground. And they lost some of their grapes too, but they will come back. And they did. But this is the way we look at our risk here at Zesty, as we look at it house by house, building by building. And we are able to do that because of the data we can get our hands on in terms of visual data now at a reasonable price. And this includes 3D data that we're then able to render and see the buildings in 3D. This enables us then with data about the events to do L1 and L2 type losses, understand their likelihood of it occurring, like a fire or hail or flood at a location, and then if it does occur, what's going to happen to that structure, based upon similar structures that experienced similar events at scale across hundreds of thousands or more houses, for instance. Lastly, a plug for our company. It's not much of a plug. We've had a few awards. I'm not going to get into this. You can feel free to reach me at any time, but I'm willing to take questions now. And this is our reality, though, is dealing with fires like this and understanding so we can predict them ahead of time so people don't have to deal with these issues as they occur like they had to in Santa Rosa 3 years ago, and including this year.
Harisha has asked, what are the resolutions of your images? Will Imagine resolution impact the risk score?
To a point. The source of the image determines the resolution. So typically for aircraft imagery, we're looking at 5 centimeters per pixel. Satellite imagery varies, but it can be anywhere down to 30 centimeters per pixel resolution. It can be as high as 50 if it's off angle a bit. But the good news is it's getting better every day. There's no question about this. I mean, even 3 years ago, you couldn't get anywhere near these resolutions. Nowhere near. In fact, it was illegal not long before that. NSA owned it all. United States, right? National Security Agency. And it was illegal to let you have data like this. So in the last few years, we've seen this transpire. Now they're putting up synthetic aperture radar satellites in LEO orbit, low Earth orbit. This is going to be amazing. And so it's just the beginning of it, but it's already clear that we get great benefit from these type of insights when coupled with other information. But like seeing these houses gone makes it very clear what happened. The same thing is true when you look at like a hurricane or any type of flood. You can easily see the damage. Hail a bit harder. Hail is more tricky. Hail is a cumulative damage event. It's not something you can necessarily see after 1, 2, 3 storms, unless it's 3-inch hail. That's one of the weird things about like hail risk is that they do happen, 3-inch hail. We had it in Calgary this last April. And what happens when hail gets that big is that it's much worse than 1-inch hail. 1-inch hail, 1 1/4-inch hail, like a golf ball, is bad, but it's only traveling about 30 miles an hour. Now when you go to 3-inch hail, 1/2 mv squared, kinetic energy, your mass goes up appreciably, is r cubed, but also your velocity goes up and more than doubles. So now 3-inch hail, 2.5, 3-inch hail can break car windows, can break windows of houses, can shred the side of your house like we saw in Calgary, and can cause appreciable damage to roofs. They'll tear shingles right off your roof. You see it when it hits the ground and it hits the street, like there's videos. You'll see it bounce 5 feet in the air, 2.5-inch, 3-inch hail, like a golf ball in the ground. It's going that fast. We're just now getting, hail is like the Rodney Dangerfield of threats. It has no respect. And yet it's 70% of the losses any given year. And so they're still trying to get their heads wrapped around in the insurance industry. And since 2008, the losses from hail have more than doubled. in the United States. You could argue that they're just ripping off the insurance industry. I don't think so. It's a mixture of all the above, but it is a real threat.
Yeah, super insightful. And I mean, like you said, the truth's in the data and the proof's in the pudding, isn't it? You know, when you can when you have these images and satellite scans, and it's like, this is how much damage was done. You can't really argue with that. And I imagine that the insights as well that Zesty is then able to attain from that and kind of maybe tweak people's policies and such, or really insightful data there. We'll jump onto a question from Maxime. Maxime has asked, as your models clearly demonstrate how different houses are correlated to one another, do you also model the risk of what actuaries describe as common shocks, so insurers that would insure multiple correlated houses will not unknowingly end up with a higher risk than expected on their books?
Yes, we look at portfolio management of various types, like reinsurance. We work with Aon and others, Zurich. Yes, it's an ongoing research topic. Certainly, you don't want to have a portfolio that's not well structured. And it's very clear that a lot of these models they've been basing a lot of their assumptions upon for many decades were made before we had big data. I know I lived through it. I was in the US Air Force in the 80s and early 90s getting my PhD in physics. And we did a lot of models that were heuristic-y, first principle physics models, even for things like nuclear weapons. Now we have the data, so we don't have to guess. And most of these older models for like fire, hurricanes, and things, they're not that accurate because you can't get that accurate for a nonlinear event. But if you can look at it statistically, you can get accurate. And you can get a much better understanding about the risk, the error bars, the confidence intervals that you're dealing with in a much more precise way.
Pat has said, nice talk. He said, do you think incorporating weather and wind patterns, humidity would also be useful in predicting wildlife fires? Also, how up-to-date are the satellite images used in the modeling, and how frequent are the models trained, and how long does it take to train the models?
A lot of good questions there. As far as wind patterns and such, we're not directly taking those into account, though those could be an aggregate, and there's many ways we could do that. We haven't to date done exactly that. But we are looking at a lot of things that one would expect, such as the fuel on the ground, the terrain, the historical patterns in the area of fires, and so forth. As far as, how often are our pictures taken, it depends upon the source. Satellites orbit the Earth every 90 minutes. They hit an area roughly twice a month. If there isn't any clouds over the area, then we get a nice image of that house again. Airplanes are scheduled as needed, so they could be after catastrophic events, they can deploy them. Airplanes do not fly during cloudy times when they can't see the ground or it's all covered snow or something. So they're more picky about when they fly, but they still get to typical sites 4 times a year. So you're looking at something 4 or more times a year, you see a structure. And so it helps you get a better idea, you develop knowledge. We can see houses adding pools. We can see additions put on a house. We can see a house being built and then lived in, so forth. So it does, there's a temporal nature to this data.
That's pretty regular. Surprising for mine. We have a question from Eric. Eric says, do you use Cooperless in your models? If so, how?
I don't think so. I'm not familiar with that term. So I guess I'll say no. We use many types of open source tools. We use all the major cloud vendors. We're up on our current deep learnings and so forth, but it's a very active space. And there's always new models we're trying all the time. We file patents and so forth and so on.
Approver has asked, is the effect of global warming taken into account while making these predictions? Great question. Global warming, it's almost like is it artificially heating up the planet somehow? Yeah, really interested there. So to repeat that, is the effect of global warming taken into account when making the predictions?
Is it explicitly taken into account? No. Is it implicitly taken into account? Absolutely. Because we're taking into account the newest data possible to make our predictions, which is taking into account the effects of global warming because they're happening more frequently, these fires. It's easy to see in the data when you've had 3 of the biggest fires in the last 5 years in California, fire seasons. That's global warming. That's pretty easy to see. You could argue, and I'm from a part of the world, Seattle, and my family was heavily involved in the logging industry for many generations. And you could argue that, well, they're not managing the forest well. And I might even make that argument sometimes. But I think it's undeniable that global warming is playing a huge part of this. And our data says that quite clearly. So we are taking it into account implicitly, not explicitly.
I want to see a bunch. Sorry, go on.
We just use the freshest data available. It's like any prediction, right? You always want to use the most current data. Whether you're predicting stocks, the price of Bitcoin, Ethereum, Ripple, or you're predicting the next hailstorm, you always want to use the most current data. And we do. We don't predict things like how many minutes till the next big 3-inch hailstorm. We don't do that. We do predict what is the likelihood of a hailstorm of 3-inch hail occurring at this location in the next year. So we do predict that. And that's a much more accurate prediction. And that's really what we're interested in doing, probability, with error bars.
YT has asked, where did the first fire start on the map? Is wind direction?
Prevalent wind direction is taken into account in the models, absolutely. Fires like to burn uphill, which you might be aware of. That is taken into account also, because they have fuel as they race up the hill, like with the Santa Ana wind. So many of these effects are taken into account, and explicitly or implicitly in the data. But that is taken into account, yes. Prevalent wind.
Awesome. Lauren has asked, are you also working in Europe?
We work with European companies like Zurich, though we're only servicing clients right now in the United States. I think that within the next year or so, we'll be servicing clients, though, on all of North America, Canada, of course. And Europe is definitely a logical place to go right about the same time. We're in talks with companies in Europe right now. We are. We're just not engaged them fully yet.
Nice one. Eric has a question. He said the University of Waterloo's Chairman Dean is the leader in the field of spatial statistics to model forest ecology and fire management. Do you incorporate spatial statistics in your models? If so, how?
We're not explicitly, well, we model and we use data regarding the vegetation types within a region. It's down to, I believe, a kilometer in size type cells. We use data from the U.S. Forest Service type data and other sources. That's one of the coolest things about right now is that we have many good data sources for this type of information. So we don't have to rely upon just USGS, though we use their data, but we use other sources also. And then in aggregate, we are able to understand better what are we looking at for vegetation. It's like the eucalyptus example that I mentioned earlier. Depending upon the type of forest as to what type of trees it is and what type of, like we have the beetle issue, the pine beetle issue, where you have a forest standing there in Colorado with half the trees dead from 3 years ago. That's kindling. And we've seen a lot of issues from that in recent years. I remember when I drove through Yellowstone when I was first going in the service in 1989. I drove through there and I was shocked at how many dead trees there were. That was 86, actually, I should say. In 89, the place burnt to the ground, Yellowstone. That's because they had so much dead wood laying on the ground. And then they saw this amazing regrowth afterwards. They saw wildflowers bloom that they didn't even know were there. And so it is a natural part of the forest to have fires. Mm. We as humans, since about 1930s, have suppressed fires as part of forestry management. And then we have issues where we get fires that are too hot. And then they cause bigger problems. A lot of these trees, like a ponderosa pine, are designed for their cones to only open after a fire. They just sit on the ground waiting for a fire to come through. And so until you have a fire, there ain't going to be no baby ponderosa pines, unless you hand plant them. So it is a part of the forest. It is. So we don't want to over suppress that. But we do take into account vegetation, and we're always willing to work with people on various research topics.
Nice. We got a question from Yasin. Yasin has said, great use of AI. From data for good perspective, I found this very interesting to help people better protect their properties. One concern, though, I am wondering about the impact on insurance cost for less fortunate households, rides in insurance cost, as well as dealing with unavoidable externalities a household should bear? E.g., what should I do if my neighbor is increasing both my risk and insurance costs? Really great question.
It's a really good question. It's a really complicated question. California is trying to deal with it proactively, but there is some interesting things even I've learned in the last year. For instance, after big wildfires like this year, what happens in a California region that's had wildfires? One might think you would increase the rules about what you have to do to protect your house. The reality is they oftentimes decrease the rules because they're worried about the people being too poor to rebuild. I think that's a big mistake. I think we should make the rules appropriate to our learnings, then have the government help subsidize those that need help. But just to rebuild where you were with even a lesser structure that's more fire prone because it's cheaper is not a very good idea. I mean, come now. So we have to be a little bit more intelligent about this. And we have seen that in California where these fires rip through, like the Tubbs fire and so forth. And then people rebuild structures that they know aren't going to survive the next fire. And maybe economics is the reason, but we know how to build structures right now that can survive a significant fire nearby. It doesn't cost that much more. It's more of an issue of usually don't put on a silly roof. You don't put on a cedar shake roof, of course. Put on a comp roof or a metal roof. If you can afford one, a tile roof, probably not. But comp roofs can survive heat. And then you have siding that's appropriate. You make sense. Maybe use stucco, things like that in a higher fire region. And then you don't have shrubs right next to your house and things like that. But there are things one can do. And there's trade-offs. And there probably would be some help from the government. I think that's a natural part of this.
If only common sense won and they were like, oh, well, we can do this to reduce your house burning to flames. Let's go the other way and actually make it easier for your house to catch on fire.
I was shocked when I learned that. I was shocked. I was like, really? You make it easier for them to build a lesser house? No, that's not a good idea. That's not something you want to do.
Maybe we'll kind of keep the politics of the U.S. policymaking. We'll leave that for another CAMDEA. That'll get everybody's blood boiling, I'm sure.
Oh, yeah.
Have you compared the weather event stats against ones from other areas with similar geography? They might help improve your model.
Yes, we have. I mean, you look at things like Appalachian Mountains, who have relatively no fires. Now, they're lower in altitude than the Rockies and the Sierras, but they've had almost no fires. I mean, Gatlinburg got a fire a few years ago. That was arson. Burnt the whole town to the ground, pretty much. Very, very sad. Beautiful area. But in general, they don't have many fires. So we do try to take that into account. The other thing that we try to do, too, is things like other threats, like hail. Hail is ubiquitous. Everything east of the Rockies is in a hail threat zone, including Calgary, as we just learned this year. So anywhere east of the Rockies, which is the vast majority of the population in the United States, can experience a hail. They've had 3-inch hail in Denver during rush hour, where it caused half the cars to not be drivable. These things do occur. They've had hail so deep in Denver that they had to bring in snowplows to pull it out. This was like in May. There was feet of hail in downtown. We've seen it in Dallas-Fort Worth, where they've had hailstorms, where they've had 3 major ones in less than 10 years, causing billions of damage per hailstorm. These storms only last like 20 minutes. So if you have one of these events occur in a really bad location, like really expensive housing, like Oklahoma City, Norman, neighborhood of it, as I understand, they had almost $1 billion loss in about 15 minutes because it hit the most expensive neighborhood in town. And it used to be, we've always had these probably, but before we had so many people, it didn't hit the expense, there was nobody to hit. Or even when there was people there, we were just lucky and went out and hit a cow pasture, knocked down sorghum or corn or something. But now we have seen a lot more of the real thing. So doing comparables is certainly a big part of this. And the more data, the better. And we want to learn from what differentiates. Is it just altitude? Is it, a lot of factors come into play here.